Okay, so the last problem involves a water coaster. So think wildebeest at Holiday World. It's zooming along, and it reaches a hill, and it needs to go up the hill. So here's my water coaster, and it needs to go up the hill, and it doesn't have enough energy to get up the hill on its own. So there is some kind of conveyor belt which is spinning here, and if you've been to Holiday World, you know that that's spinning. And as the raft hits it, it adds energy to the raft by applying a force, and that gives it extra energy. Okay, so this is what physics teachers do when they're bored, standing in line, they make up problems. So I'm going to call the bottom of the hill h equals 0, or y equals 0. So we're going to start here, and we're going to end there. So the problem has the following variables. The initial height is 0 meters. And the final height, which is how high it is when it's here, it says the hill is 5 meters high. So the final height is positive 5.0 meters. The initial velocity is how fast the raft is going before it encounters the hill. And we're told that is 6.0 meters per second. The final velocity is how fast it's going at the top. And that's what we're after. The mass of the raft, including the riders, is 250 kilograms. And the system, energy is added to the system when it hits the conveyor belt, and about 10,000 joules of energy is added as it skips along the conveyor belt. Okay? And we want to know how fast is it going at the top. So we are going to start with our big principle. We are going to apply the principle of conservation of energy. So ME final, the energy at the end of the problem, is equal to the energy at the beginning plus any work that was done on the system. For this problem, that means that 1/2 the mass times the final velocity squared plus mgh final must equal 1/2 the mass times the initial velocity squared plus mg times h initial plus w. Okay? Now, because the initial height was 0, there was no potential energy at the beginning of the problem, so this term goes away. But it's the only term that goes away. So now, we need to solve what's left for the final velocity, which is right here. So to do that, I'm going to do a couple things. First of all, I'm going to clear the fraction by multiplying everything by 2. And while I'm doing that, I'm going to divide every term by m. Okay, now I can't just go cancel all the m's because we've got w over here and there's no m in the w, so I can't cancel them all. So to clear the fraction, I'll multiply everything by 2, and then I'm going to divide every term by m and see what I'm left with. So when I do that, I'm going to get, let's see, the final velocity squared. When I multiply 2 over m times this, the 2 cancels the 1/2, the m cancels the m, I got final velocity. When I multiply this by 2 over m, I get plus 2g h final. Sorry, the lights in my room just went off. So this is the left side of the equation, equals, when I multiply this by 2 over m, I get v initial squared. And when I multiply this by m, I get 2w over m. Okay? So to solve this, I need to bring this to the other side. So I'm going to get v initial squared plus 2w over m minus 2gh final. And that's the final velocity squared. So I'll get the square root of that. Okay? And then, when I plug in all my numbers, the initial velocity is 6 squared plus 2 times 10,000 over 250, and then minus 2 times g times the final height, which is 5. You plug in all those numbers, and you get a velocity of about 4.23 meters per second. Okay? So this right here is an expression for the final velocity, and then given the particular set of numbers we got, that is the answer to the problem. Okay, so again, same idea. You apply the work energy theorem, but in this case, the work is not 0. And so when the work is not 0, be careful. The mass does not cancel everywhere. You can't just ignore it. You got to keep it in there. Okay?